Math 1314, Tyler Junior College, Section 4.3, Properties of Logarithms. The next rule. If you're wondering why I called it the next rule and put quotes around it, it's because I didn't want to give away the ending. Towards the end of the video, I'll cross out the word next and replace it with the correct word, because replacing it with the word would kind of spoil how this is going to turn out. So what would be a natural question to ask once you've discovered and established the product rule, which says the sum of two logs with matching bases is equal to the log of the product of their arguments? The sum of two logs with matching bases is equal to the log, same base, of the product of their arguments. What about the difference? In other words, what if instead of adding two logs with the same base, I subtracted them? Now, you may already know this rule. You may be able to guess what the right side is. But sometimes when you're making conjectures and proving things in math, you may not know what's over there until you run into it. So how can we possibly encounter what would happen on the other side of that equal sign? Well, how did we prove these two things were equal? We took a one-to-one function, f of x equals b to the x. We substituted each of these into that function and showed that their outputs were the same. And in a one-to-one function, equal outputs means that you had equal inputs. Now, I don't know what the other side of this would be, aka the second input, but let's see what happens if we take the left side and treat it as an input for the same function. So let's start with the same supposition as before, that f of x equals b to the x power. Same stipulations on the base. It's greater than 0, not equal to 1. That's kind of always assumed for logarithms, but it's never a bad idea to state the obvious. You want it to be impossible to misunderstand. Then let's see what happens if we put the difference of two logs into this function. So f of log base b of m minus log base b of n. Well, this function says give me something and I'll stick it as an exponent on b. Okay. Stick all that in the exponent. B to the log base b of m minus log base b of n power. Don't be intimidated by the mess of symbols over here. Try to focus more on the structure of what you're looking at. This is b to a power, but the power is the difference of two things. So what you're thinking at this point is, do I have a rule that either starts or ends like this? In other words, do I have an exponent rule that says now's the time to subtract exponents? The answer is of course there is. B to the x over b to the y power. That's the setup exponentially that says now's the time to subtract powers. But anything we can put together, we can take back apart, loosely speaking. So if we work this exponent rule by disassembling this exponential expression as a ratio of two exponential expressions, in other words, if we work this rule in reverse, it says that b to this difference exponent is b to 1 power over b to the second power. The power in the numerator is the left side of the subtraction problem, so log base b of m. And the power in the denominator is the right side of the subtraction problem, so log base b of n. Well, both of these are just that fourth and weird property over there that says the base and the log cancel, which means this is equal to m over n. So I know what the output is for this, but is there something else that would give the same output? Now this is where, when you're proving things, you either have to have insight or a previous frame of reference. In our case, the previous frame of reference was the proof in the previous video. When we proved that these were equal by substituting both of these into the same function that was 1 to 1 and getting equal outputs, we concluded that the inputs were equal. In other words, these were the same. But when we put this into the function, it was easy because everything canceled and we just got left with that. So how can we reverse engineer this to replicate that result but kind of in reverse? What if I took b and raised it to a log base b power? That would end up giving me this. Well, this is the same construct that says everything cancels and whatever here is what you're left with. So if I were to reverse engineer it, I would have to put m over n here. These are equal by doing this property in reverse. Well, isn't this just f of log base b of m over n? Yeah, this function says give me something and I'll stick it on b as a power. Well, I gave it something as a power, so that must have been its input. Well, look at the very beginning and the very end of this long run-on equation, equality, if you will. If you summarize it, putting this into the function equals putting this into the function, and this function is still 1 to 1, which means if the outputs are equal, that's what this is saying, the outputs of these are equal, then the inputs are equal. Therefore, the inputs are equal. Log base b of m minus log base b of n, the first input, has to equal the second input, which is log base b of m over n. Now some of you may remember this rule. You may have figured it out by saying, oh well, when this is plus, this must be times, so when this is minus, this must be divide. But if you're doing upper level math, you can't just say, well, obviously it's true. You or somebody else has to first prove it. But in this case, we have. And now we have a second rule. And what should we call this rule? Well, this was called the product rule because we took the product of the arguments. You could call this a fraction or a ratio, but if you think of it as a division problem, you could call it a quotient. This is called the quotient rule, which is what the word next is going to change to. And it's worth mentioning that for both of these, the m and the n both have to be greater than 0. Otherwise, you have logarithms that are undefined. And again, in most college algebra classes, you probably would not be asked to prove this, but this isn't most college algebra classes. For those of you who are just like, I don't need to take upper level math classes, I just need to know how to do the math. Don't worry, I'm going to get to that in the next video. But I'm a firm believer that most people are capable of doing more math than they give themselves credit for. Not just doing math, but discovering it, making conjectures, and even proving that they're true. Now I'll admit, proving something takes lots of experience, lots of practice, lots of examples to build techniques, and that's what I'm kind of doing right now for those of you who are planning on taking more upper level math classes. In the next video, we're going to discover one more rule. Actually, I'll just tell it to you. I think we've done enough discovering and proving. We'll list one more rule. It'll be a short video, and then we're going to put all of them into action.